I'll tell you what, tonight's not going to be too overly challenging, I don't think. We're basically going to take a variety of ideas that you've already mastered and kind of combine them together. You've already done really well with definite integrals as far as using your first fundamental theorem to find the numerical value. You've already done a really good job with u-sub. And tonight, last night we did u-sub with indefinite integrals. Tonight we're going to graduate to putting bounds on those integrals and creating definite ones. So now the theme, though, as you go through tonight, I need you to keep telling yourself one thing, and that is to make sure everything has to be in terms of u. And I mean everything, okay? Has to be in terms of u. Specifically, I'm going to put a little asterisk here. We've got to make sure we rewrite the bounds so that they're in terms of u as well. The given numbers that they put on there, as initially everything's in terms of x, we've got to change everything and make sure it's in terms of u. So similar to last night, I'm actually going to look at a live example first of all. And then what we'll do is we'll go back and we'll make a few notes about what we just did. But anyway, let's do an integral from 0 to 1, and our curve is x times the quantity x squared plus 1 cubed. Okay? And I'm not exactly sure what this function looks like, but we're certainly going to go ahead and find the area bounded between the curve and the x-axis. My inner function right off the bat is going to be x squared plus 1, because that's the quantity that's being cubed. The derivative with respect to x is 2x times dx. Divide the 2x over to get the dx isolated. We're going to go ahead and we're going to make this substitution in for dx. Again, the u is going in for x squared plus 1. So here we go. I've got my integral. I'm not going to worry about the bound yet. I'm going to postpone that for the time being. And I've got my u to the third, and I've got my du over 2x. So the good news right now is that this x here is going to cancel out with that x. And life is good. We were able to cancel out all the x's. Now let's talk about those bounds that we desperately addressed early on. We said, like, right now this is x equals 0. Okay, think of it as x equals 0. And this one up here is x equals 1. All right, I need the bounds to be in terms of u as well. So I need to look at this definition I wrote, u equals x squared plus 1. I'm going to take my lower bound of 0 and I'm going to substitute it in for x. And I've now created a new lower bound of 1. I'm also going to do the same thing with my upper bound. Substitute that upper bound, and I've now got a new upper bound of 2, because the bounds also have to be in terms of u. So let's go ahead. We'll rewrite. We got a coefficient of 1/2. We've got bounds from 1 to 2, u cubed du, and now we're gonna do everything in terms of u. So u to the 4th, and I divide by the new exponent. So my coefficient's 1/8 now. And I'm just going to plug in the bounds 1 to 2. Notice, okay, we are not rewriting these antiderivatives so that they're in terms of x. Okay, we're not doing that. We're just going to go ahead and we're going to plug in our bounds, and that's the big benefit of rewriting the bounds in terms of u. So I've got my 1/8, and you could leave the 1/8 outside and just go 2 to the 4th minus 1 to the 4th. Let's see, 2 to the 4th is going to be 16 minus 1 is 15. So how about 15/8 is the numerical value of that definite integral. So like we said on that first slide, our big theme tonight is a complete change of variables. We're going to rewrite everything in terms of u. So for instance, just to get the just to get the right terminology down, if we were integrating from a to b, and we were integrating, remember, f prime of g of x times g prime of x, the answer here is going to be the integral of f prime of u with respect to u, and the new lower bound is going to be g of a. And you're wondering, where did that come from? Well, remember, we said u is going to be g of x. So I had to plug my a into that function to create the new lower bound. And then I had to plug b into that. So g of b is my new upper bound. So if you think of g of x as our inner function, we're going to plug the bounds into that and create the new bounds. Alright, our second example, let's say that there are bounds of 1 and 5 right now. And let's say I've got 1 all over radical 2x minus 1. So very innocent looking integration here. We do quickly identify our inner function as being the quantity 2x minus 1. So if we differentiate with respect to x, we'll get this, divide the 2 over, bada bing, bada boom. So we're rocking and rolling, and I've got the integral of 1 over radical u times du over 2 if I make all my appropriate substitutions. Now let's address the bounds. If I plug in the lower bound, I end up getting the same result. But now when I plug in the upper bound, 2 times 5 minus 1, I'm going to end up with a new upper bound of 9. And that's going to be a pretty friendly number, actually. So let's go ahead. We'll pull out the coefficient of 1/2. We've got our new bounds of 1 to 9. I'm going to rewrite this expression here as u to the negative 1/2. And we're ready to rock and roll. Things are falling into place very nicely here. I'm going to add 1, so my new exponent is 1/2. I'm dividing by 1/2, which is the same thing as multiplying by what? Yeah, 2. So if I multiplied my pre-existing coefficient by a 2, I've now got a new coefficient of 1. Bounds of 1 to 9. And these bounds couldn't be any nicer. So we've got radical 9 minus radical 1. 3 minus 1 is 2. Alright, for our next problem, we're going to do almost the same problem as we just saw. Alright, I've still got bounds of 1 to 5. I still got radical 2x minus 1 on the bottom. But I'm going to tweak the numerator. I'm going to put an x there instead of the 1 that was there in the last problem. And we're going to address this big question right here. What happens if we can't cancel all the x's? And you're probably wondering, like, what does that, what do you even mean by that? Well, let's take a look. I've still got the same inner function. If I differentiate, I still get the same derivative, of course. Move the 2 over so that the dx is by itself. Watch what's happening here. So I go ahead and I got, my new bounds we already proved were 1 and 9 after I plugged them into this expression. I've got x over radical u times du over 2. Do you see the problem? There usually was an x right here so that I could cancel this x out with this x. Well, the problem is there's no x down here, so it's impossible for me to make that cancellation. And that was one of our golden rules with u-sub, is when we got to this stage of the game, we had to make sure that all of the x's canceled out. So we've got ourselves a problem. And we'll go back to the very first thing you put in the notebook tonight. What was the very first thing you wrote? Everything has to be in terms of u, and there are no exceptions to that statement. Well, what we're going to do is we're going to piggyback off this statement right here when you said u is equal to 2x minus 1. I want you to solve that for x. So we could say maybe u plus 1 equals 2x, and then divide the whole thing by 2, right? So now you've just proven that x is equivalent to u plus 1 over 2. And that's the substitution I'm going to make right now. So we're going to say, all right, we've got the integral from 1 to 9, and you know what? I'm going to bring this u up to the top. I'm going to say u to the negative 1/2, and then I'm going to make my substitution for x, and I'm going to say 1/2 of u plus 1/2. Notice I rewrote it a little bit differently because what I did is I kind of made like a beaver and split that bear up. I don't know if that helps or not. And perhaps maybe it doesn't, because I'm looking at my next move. My next move is I'm probably going to want to pull out a GCF. And let's see. I believe my GCF on the inside here is a 1/2. If I pulled it out, I would multiply by the 1/2 I already had here. So I have a new coefficient of 1/4. And then what I'm going to do is I'm going to distribute this term through the parentheses here. After I've already pulled out that 1/2. So it's going to be u to the positive 1/2 plus u to the negative 1/2. And we can celebrate here because we've officially rewritten it in terms of u, and we've got everything expressed as friendly as it possibly could be. So now I'm ready to integrate. And I'm going to add 1 to the exponent, multiply by the reciprocal of that exponent. And let's see, u to the positive 1/2 times 2. Bounds of 1 and 9. Notice how I just left the 1/4 all the way out front. Let's see, 1/4. Now what I need to do is I need to plug in the 9. So let's see, that's going to be 2/3 times, let's do square root of 9 cubed plus 2 times the square root of 9 minus 2/3 square root of 1 cubed plus 2 radical 1. Woo! Man, we got some number crunching going on here. This is intense. All right. Let's see. Square root of 9 is 3. 3 cubed, 27. How about 54/3? Oh, that works out pretty nice, actually. I think we're going to get a real nice number there. And 2/3 plus 2. Okay. All right. 54/3. What the heck is that? I think that's 18, if I do believe. So let's see. We got 18 plus 6 is going to be 24 right there. Minus, now let's see, this is really 6/3, so 8/3 right there. Let's see here. That's going to be, if I multiply by 3, that'd be what, 72/3 minus 8/3 is going to be 64/3. 4/3 times 1/4. 4 goes into there, 16. I'm saying 16/3 is my final numerical answer. And that's fairly common. Probably the most intense part was the latter half where it was all number crunching and just staying organized. You don't want to get nipped down here. You don't want to do everything, all the calculus perfectly and then screw it up on the arithmetic here. So be really careful with all your number crunching. All right, let's see if we can't practice one more. And, wouldn't be a good finishing problem if it wasn't a messy one. So let's go with x cubed root of x plus 6 with respect to x. Okay, so we've clearly identified, whoops, I need some bounds on this, don't I? Let's try -5 as a lower bound. And let's try +2 as an upper bound and see how crazy that gets. Okay. So we've identified the need for u sub. We're going to let u equal the inner function because we do see a composition. And the derivative is simply dx. I tell you what, I put a little smiley face there just because there's no extra coefficients involved. We're ready to rock and roll. Alright, let's see. If I plugged a -5 into this statement here, I'd get a new lower bound of 1. And if I plugged a 2 into there, I'd get a new upper bound of 8. Those are very friendly numbers to work with, believe it or not. I still have this x, I've got the cubed root of u, and then I have a du being substituted for dx. Piece of cake, right? Well, what's the big problem? We weren't able to kill all the x's, alright? We've still got this x still alive, and we need to rewrite him in terms of u. So what I've got cooking here is, let's say, based off of this statement right here, we could say that u minus 6 is equivalent to x. So I'm going to go ahead and make that substitution here. Still got bounds of 1 to 8, we've got u minus 6, we've got our u to the 1/3 on the outside, and we're ready to distribute. We're getting so much closer to our final answer. If I distribute, I'm going to add the respective exponents. And we're going to be ultra careful here as we integrate. If I add 1 to that 4/3, now I'm really adding 3/3, so that's now 7/3. My new coefficient would be 3/7. And minus, let's see, how about u to the 4/3? Divide by 4/3 or multiply by 3/4. 6 times 3/4 is going to give me 18/4. And of course, I'm going to reduce that here in a second. Bounds of 1 to 8. All right. Ooh, baby, I feel like some big numbers coming on here. So let's say 3/7 times, all right, it's going to be cubed root of 8 to the 7th. Cubed root of 8 is a 2, so I've got to do 2 to the 7th. Minus, let's see, that's 9/2. 2 to the 4th would be 16. Minus, all right, I love plugging 1. 1 raised to any power is simply 1, so I'm going to get 3/7 minus 9/2. And I tell you what, ladies and gentlemen, I'm going to trust from this point on that, it's not the cleanest number crunching, but we're certainly capable of it. 2 to the 7th is a big bear, maybe, let's see, how about 128? But we could definitely get through the number crunching if we had to. Well, before I leave you tonight, I want to repeat this one more time. What was our big theme for tonight? We're going to walk away from this video with one big picture item in mind. What was our big theme tonight? Let's make sure when we rewrite these problems, everything from the bounds to the dx, everything must be in terms of what? Must be in terms of u. And let's put a big exclamation there, okay? So that's really going to take care of business for tonight. Hope it went well, and we'll see you tomorrow.